Hi, everyone. This is Jinghao. So I'm a PhD student from UIUC working on operating systems. Today, I'm going to show you how we can design a kernel probe mechanism that is trapless and make kernel instrumentation much more efficient. So kernel probes, or Kprobes, is an observability primitive that allows users to dynamically instrument almost any kernel instructions using a custom handler function. And because of its dynamic nature, there's no kernel rebuild or reboot required. And therefore, it is widely used in tracing and debugging. So the performance of the kernel probes are important. This is further exemplified by our use case, where we're trying to use Kprobes to implement a kernel control flow integrity mechanism, where we place one Kprobe on each indirect call instruction and validate the indirect control flow transfers. So the basic Kprobes are implemented by traps. Whenever we register a Kprobe onto the probe target, the kernel will make a copy of the target and replace the original one with the trap instruction. On x86, this is an int3 instruction. And when the execution hits the int3, an interrupt occurs, and then the kernel context switches to the interrupt handler. Inside the interrupt handler, the kernel will execute the user-provided Kprobe prehandler. After this prehandler, the kernel single steps this copied probe target. The single step itself is implemented using a second trap. After the second trap, the kernel executes the Kprobe post handler, which is also provided by the user. And after that, the execution returns to the next instruction. As you can see here, there are two traps being used, which incurs significant overhead. And in fact, we measured a single kernel probe that takes more than 6,000 cycles. So that naturally makes us wondering that how can we build a fast kernel probe mechanism without using traps? So in this paper, we make the following contributions. We build UNO Kprobe, which is a fast and universally trapless kernel probe mechanism. UNO Kprobe can increase the performance of a single Kprobe by a factor of 10, and that of the Kprobe-based KCFI reinforcements by a factor of 3. We implement UNO Kprobe on top of the x86 Linux Kprobe. The Linux Kprobe already had some ad hoc optimizations. We identified and addressed these fundamental limitations in the existing optimizations and integrate our work with the existing optimizations. And if you're interested, our code can be found on GitHub. So the basic design principle for trapless Kprobes is to replace the traps with direct control flow transfer instructions, such as calls and jumps. Well, one naive way to do this is to use no-ops to allocate extra space at compile time so that later we can feed those instructions in. The way we can do this is to insert a 5-byte no-op before every kernel instruction at compile time. And then at runtime, we can rewrite the no-op into a 5-byte call instruction that transfers the control flow to the Kprobe trampoline. And this trampoline will be responsible for setting up the call to the actual Kprobe handler. So let's take a look at this code example. Here, we insert a no-op before every kernel instructions. And then when we register a Kprobe, let's say onto the move instruction, we can rewrite the preceding no-op into a call instruction that jumps to the Kprobe trampoline. Note that the use of the call also makes it easier for us to return to the next instruction, because a ret will be enough. However, because we inserted all these no-ops, that actually leads to performance issues. Well, specifically, we measured a 30% performance overhead from the no-ops on LE bench without any Kprobes attached. Well, our key insight is that the majority of the no-ops are actually not necessary. And in many cases, this target instruction can be directly rewritten into a jump instruction without needing the extra space from the no-ops. Taking our previous example, here, we can directly rewrite this move instruction into a jump that jumps to a per Kprobe trampoline. And this trampoline will invoke the user-provided Kprobe handler, and then execute the copy of our probe target, and finally jump back. You can see that here we use a jump instead of a call. This is because the return address of the call always points to the end of the call instruction, which, if we have this in-place rewrite here, may not be an instruction boundary. Instead, using a jump gives us more flexibility on which address to jump back to. However, the problem is that such jump rewriting does not always work. Specifically, it falls under two cases. The first case is that we may not have enough space to avoid overwriting other branch targets. In such a case, the inserted jump will span basic block boundaries, which means it will overwrite the start of the second basic block, which is a branch target, and break the instruction decoding process there. So still taking our previous example, but now let's say instead of that move instruction, we have this shorter add instruction. One thing to note here is that this JNE instruction jumps to the first byte of this inc instruction. So if we were to blindly rewrite the add instruction into a jump, because the jump is longer, it's also going to overwrite the first byte of this inc instruction. So the next time the JNE jumps to this byte, this is no longer an instruction boundary, and it cannot decode the inc instruction correctly. Such a problem is inherent in a variable length instruction set architecture such as x86. And the second case is that there are address-dependent instructions that we cannot just copy and execute on the trampoline. This is because the text address of these instructions matter. This includes the instruction pointer-related instructions, because they often use their own address to calculate the jump offset, as well as the page fault triggering instructions. This is because the kernel uses the address of these instructions to handle page faults. So the high-level idea of UNO Kprobe is to selectively insert no-ops at the place where we cannot directly rewrite into jumps, which are the cases we just talked about. So in UNO Kprobe, we perform our needed no-op insertion using an LLVM machine IR pass. This is because at this point, the basic blocks are explicit, and also the LLVM MIR closely models native code, which gives us more information and control over the code generation process. We further integrate our design into the current x86 Linux Kprobe implementation and its existing optimizations. And finally, we implement a more space-efficient Kprobe trampoline for UNO Kprobe on Linux. Now, let me show you how we can selectively insert the no-ops using LLVM. So here, the LLVM MIR of our previous example is shown in this code snippet. Our pass runs at the end of the LLVM code gen pipeline. So at this point, the instruction selection is pretty much done, and we can easily identify those address-dependent instructions based on their opcode, such as this JCC and this write instruction here. And then we can insert the no-ops accordingly. For the case where we do not have enough space to avoid overwriting other branch targets, we insert the no-op before the last instruction of the basic block. So the Linux Kprobe actually already incorporates the jump-based optimizations. However, due to various reasons, those optimizations are only ad hocly applied. And as a result, there are still around 21% of the kernel instructions that are not eligible for Trapless Kprobes. When we apply our UNO Kprobe design on top of the Linux Kprobe, we focused on those non-optimizable cases and used our compiler paths to identify and patch them with no-ops. So for a Trapless Kprobe mechanism, a trampoline is always required. This is because we need to save the current registers before the Kprobe handler invocation in order to prevent the handler from corrupting the current context. The problem is that the trampoline in Linux's jump-based optimization is not scalable. So this is because when we replace the instruction into a jump, we always need to copy it onto the Kprobe trampoline. And because this prop target it's unique for each Kprobe that effectively makes the trampoline a per Kprobe trampoline, whose memory usage scales linearly with the number of Kprobes. In contrast, UNO Kprobes executes this probe target in place. And therefore, in our implementation, we only need a global trampoline that takes a constant 96 bytes in kernel memory. So we evaluate UNO Kprobe on its coverage of Trapless Kprobes. And what we found is that around 96% of the kernel code can now enjoy Trapless Kprobes. This is up from the 79% in the existing Linux Kprobe. And for the remaining 4% of the kernel instructions, those are the ones that cannot be easily processed in LLVM. For example, the assembly source code, as well as the instructions that may trigger page faults. And UNO Kprobe can increase the performance of a single Kprobe on an instruction that is not optimizable in the existing Linux Kprobe by a factor of 10. We also measured the overhead from those no-ops. And we found that on average, on LE bench, there is around 10% overhead from these no-ops. So now, let me show you the performance improvement on our KCFI use case. So here, the x-axis are the benchmarks in LE bench. And the y-axis is the runtime over the case where no KCFI is applied. We measure the performance of KCFI implemented by both the existing Linux Kprobe, which is shown by the orange bars, and UNO Kprobe, which is shown by the green bars. What we found is that UNO Kprobe provides a 1.4x speedup over Linux Kprobe on average across LE bench. And for certain cases like POE, UNO Kprobe can achieve a speedup up to 3x over the Linux Kprobe. And throughout the course of the project, we also upstreamed improvements to the Linux Kprobe. Those are merged and released in Linux version 6.9. To conclude, we built UNO Kprobe, which is a fast and universally trapless kernel probe mechanism. We implement UNO Kprobe on top of the existing Linux Kprobe and integrate our design with the existing optimizations. We found that UNO Kprobe can now cover 96% of the Linux kernel code with Trapless Kprobes, with a single Kprobe now runs 10 times faster. So if you're interested, our code can be found in our GitHub repo. Thank you, and I'm happy to take any questions.